And today I'm going to talk about the fuzzy algorithms for FCI excited states. And this is joint work with quite a few people, Wei Guo, Bicheng from Fudan, and Jianfeng from Duke. And Zhe was previous graduate student at Duke. Now he's in finance kind of company. And so we are going to talk about the FCI. So we will start from the Schrödinger equation. So the time-independent many-body Schrödinger equation is nothing but a linear eigenvalue problem. Here, H hat denotes the Hamiltonian operator, psi is the wave function, E is the energy. And the difficult part comes from the many-body. So when we say many-body, we mean the wave function is a function of R1 to Rn, and for Ri as in coordinate in 3 dimensions. And this is n denotes the number of particles. Here, I mean, we will focus on the electronics system. So n is the number of electrons. And under Born-Oppenheimer approximation, the Hamiltonian operator with Q nuclei and electron is denoted as the following formula. The first term is the kinetic. So this is the kinetic part for the electron, and also the kind of potential, or the potential from the nuclei, and also the Coulomb interaction between electrons. And due to the symmetry, okay, so this is not only many-body, there is also underlying symmetry, and that is well-known anti-symmetry, which means when we swap 2 positions, the wave function, you have a negative sign in front of it. So a natural kind of discretization or natural basis for such a symmetry, and also the many-body wave function, is the Slater determinant. Okay, so let's assume we are given phi 1 to phi m as an m orthonormal one-body basis. Then a Slater determinant is just put those kind of choose n out of m and put them as a Slater, as a determinant. Okay, and this naturally we know when we swap 2 positions of Ri, then it's equivalent to swap 2 columns of the determinant, and then you get a negative sign. So once you are having bases like Slater determinant, you naturally have anti-symmetry embedded. And also this is the many-body wave function. So, but I mean, if we pick n out of m, then the total number of bases for this FCI problem will be on the order m choose n. So this is a gigantic kind of problem. And we denote it as D1 to Dn FCI. Then the ground state and also excited state is just a linear combination of such things. And here we use Cij to denote the coefficient of the representation. Okay. And how difficult is this problem? If m is 48 and n is 10, then the problem size is about 10 to the 8. And memory cost for a single vector will be 1 GB. But if we increase it a little bit, let's say we have 56 orbitals and 14 electrons. 14 is something like nitrogen dimer or carbon dimer. Then the size will be 10 to the 11, and memory cost will be 10 terabytes. Okay, so for 1 terabyte memory, we can still find machines nowadays. And I mean, nowadays, the largest single node machine will be about 10 terabyte. And for shared memory machine or distributed memory machine, roughly we can find about 100 to 1000 terabyte. Okay, but if you have 84 orbitals and 48 electrons, then the problem size will be 10 to the 10 to the 22. Then this is roughly 10 to the 11 terabyte. So it's not possible to store such a matrix. Not even matrix. I mean, it's not possible to store the entire wave function as a vector. Okay, so we must find some way to compress it. And the good thing for this problem is that due to this special structure in the Hamiltonian, okay, we can decompose it into 2 parts. One is a single excitation, one is double excitation. And single excitation only act on single one-body kind of a single wave function. And double excitation kind of affect 2 coordinates, 2 Ri and Rj. And hence, there is a kind of huge sparsity in the Hamiltonian matrix. So let's assume we are given 2 Slater determinants, Di and Dj. So if they only differ by 1 coordinate, so I mean, Di will mean this is some orbital are occupied, others are not. So if they only differ by a single coordinate, single kind of orbital, basis, one-bit basis, then the corresponding entry is non-zero. If they differ by 2 and exactly 2, then this is also non-zero. However, if they differ by more than 2 kind of orbitals, for example, we remove OPQ from DJ and add RST to DJ, then the corresponding matrix entry is 0. So roughly speaking, I mean, the matrix size grows factorially, but the number of non-zeros per column is m squared times n squared, on the order of m squared times n squared. Okay, so this is an extremely sparse matrix. And what we want is to find the low-lying eigenvalues and eigenvectors for this sparse matrix. And I mean, we define a few terminology so that we can describe algorithm later easier. So we say DI is H connected with DJ if the corresponding matrix entry is not 0. And let's pick the column of DJ. Then, I mean, we use this script J sub H of J to denote the set of non-zero entries. Okay, the indices of non-zero entries on the J's column of the matrix. Okay, so these are basic setup. And let's summarize it a little bit. So full CI problem from kind of numerical linear algebra point of view, or from, I mean, it's just a sparse symmetric eigenvalue problem. H is the corresponding sparse matrix, and C is the eigenvectors, and lambda is a diagonal matrix with eigenvalues on its diagonal. And full CI provides numerically accurate solution to Schrödinger's equation, and the only approximation we did is the truncation of the basis set. Okay, and full CI is invaluable in benchmarking approximate quantum chemical methods, especially in the case of bond breaking reaction, first row transition metal. Essentially, I mean, it's very important for strong correlated system. And full CI is used in many embedding methods, just as a solver for the kind of embed part. And the matrix size grows factorially with the number of electrons and orbitals. And each matrix evaluation is relatively expensive because, I mean, the absolute value of each matrix entry is actually known in advance. However, we still need to calculate the sign before that. And the calculation of the sign takes some kind of operations. It's not order 1. Okay, it's actually on the order of number of orbitals. Okay, and I mean, of course, there are many existing work to address such an eigenvalue problem. From numerical linear algebra, there are traditional eigensolvers, for example, power method, Lanchos, Davis, and log PCG, PPCG. And these methods are kind of more well known in the DFT world because they are kind of efficient. But I mean, the problem size, the eigenvalue problem size in DFT and full CI are dramatically different. So here we say they are only for small problems in the sense of full CI, in the sense comparing to the 10 to the 22. Okay. But still, I mean, they are efficient algorithms for problem size of 10 to the 10 to the 4, 10 to the 5, 10 to the 6. Okay. And if we take the problem size into consideration, there are many methods from the chemistry. And the first class of method is based on Monte Carlo. And the most well-known are FCI QMC, which is the first full CI Monte Carlo method. And later there is IFCI initiated, and also SFCI. And since there are Monte Carlo type of method, so there's bias and variance trade-off. And the variance in general is large due to the sign problem. So later we will see the numerical result of that. And if we extend it to kind of excited states, okay, essentially we have more columns for such a problem, then one difficulty for Monte Carlo method is that the orthogonalization among columns will be difficult to conduct. And what they did is just do a few steps of Monte Carlo, then kind of orthogonalize those particles, and then also kind of iterate between these two steps. And there is another family called selected CI, essentially find the important coordinates of the matrix and restrict the problem to the principal submatrix. And then, I mean, just solve the eigenvalue problem of the principal submatrix. And these methods are, I mean, there are methods like hit-best CI, ACI, ASCI, etc. And I mean, in many of those implementations, they store the submatrix. They store the principal submatrix in memory. So they have a huge memory cost. And if they don't do that, then the difficulty will lies in mapping the coordinate. So since we select a few principal submatrix, and then we do not have a natural ordering of the selected coordinates, then the ordering or how to order those kind of selected coordinates will be a issue there. Okay, and another well-known method is DMRG, density renormalization group. Okay, density matrix renormalization. And later we will see that, I mean, the convergence is not, I mean, is not as efficient as some of those kind of FCI methods. Okay, although, I mean, they asymptotically that grows kind of linearly with the system size. Okay, and what we are going to talk about today, we will mainly describe two methods. One is in the coordinate descent family is coordinate descent method for excited states calculation. And towards the end of that, we will show some kind of drawback of that method, and which kind of motivate us to develop the next method, which is triangularized orthogonalization-free method. And yeah, so the second method is still kind of under developing. So we just apply to kind of small size problems, and later we will extend it to kind of FCI problem from practice. And we also have another kind of parallel method to the triangularization-free method, which is so-called weighted trace penalty minimization method. And due to the time constraint, we might not be able to introduce that. Okay. So first, coordinate descent FCI. And this is an extension of our previous work of the CDFCI for ground state. And when we extend it to the excited state, this is something of admits the given formula. So now we, instead of a single vector, we have a matrix. So C is now a M by K matrix, and this C transpose is nothing but, I mean, a row matrix. And this is objective function. So we view the eigenvalue problem as an optimization problem, then address the optimization problem using coordinate descent method. So this is the essential idea. And further, we also kind of contribute to the how to select coordinate, how to compress those coordinates, etc. So the gradient of such an objective function admits the following formula. So this is 4HC plus 4C times C transpose C. So, I mean, as we can see, if gradient equal to 0, then C must lie in an invariant subspace of H, because this is a K by K submatrix. So this is nothing but, I mean, kind of transforming these columns, but still lies in the columns of C. So C must be formed by eigenvectors of H. And if further kind of analyze this thing, and this is non-convex problem and unbounded Lipschitz constant. So those things create a lot of trouble in analysis. And the local minimizer of this problem is just the V is eigenvectors, low-lying eigenvectors, and lambda is the corresponding eigenvalues on the diagonal. So the local minimizer will be of form V times square root of negative lambda. We assume those lambda are negative. So this becomes a positive diagonal. And V times square root of that. And another thing is that we also have this Q. Okay, this Q becomes an arbitrary orthogonal matrix, because if we substitute this Q into the middle, then they cancel with each other. So for different Q, let's say if we have Q1 and Q2, when we substitute those expressions into the objective function, then we find they admit the same value. Okay, so this also implies that all local minimizers are actually global minimizers. So which makes the problem easy, but this Q actually creates a lot of trouble to the method. So we will discuss that towards the end of this part. Okay, and so as a fourth order polynomial, f is a first order polynomial. So we can address such a kind of line search problem. So if we assume, yes. Mm-hmm. Here, yes, we assume. I mean, so the thing is that we only assume there's a gap between k and k plus 1. Yeah. So I mean, for this method, we didn't assume the eigengap among k. So I mean, from k to k, from 1 to k, there could be kind of degenerate eigenvalues. Okay. Yeah. And then I mean, we have this kind of I mean, since we want to address this problem using optimization methods, so line search will be a great help. And then we write down the line search problem. This is C plus EJ times alpha tilde. And alpha is a row vector of length k, and EJ is just one on the j's coordinate. So here we essentially mean we update a single row of the vector, okay, the jth row of this vector. And then we can write it as an optimization problem of for variable of size k. And for this problem, we can write down the gradient on the auto Hessian. And the gradient is admit this form. And why we color those kind of coefficients? Because all these coefficients can be evaluated efficiently, which means this for this kind of third order polynomial, we know the coefficient kind of in order k cost. So this is Cj, this is Cj, just jth row of the vector, and this is C transpose C. And we didn't calculate it online, but we just updated this quantity. So this quantity is actually stored as a whole, and we just gradually updating this value. And this Cj transpose Cj can be evaluated. This is just diagonal of the Hamiltonian, and this is nothing but put three terms together. And here we have Bj. Bj is h times c, the jth column of h times c. So Bj is also updated gradually. So when we update C, we also updated Bj. So Bj, B and C are stored as two vectors, and C transpose C is stored as a k by k matrix. Okay. And if we take a look at the Hessian, we know those coefficients are also easy to calculate. Okay. And this is a kind of third order polynomial, and we want to minimize fourth order polynomial, we want to minimize it. Unlike, I mean, single coordinate case, unlike one column case, we can just solve this third order polynomial, which can be easily solved. Here, we need to apply a Newton method. That's why we also evaluated the Hessian. Okay. So we essentially apply a Newton method to solve this kind of minimization problem. Okay. And the initial value is actually comes from the gradient. So we assume this is alpha tilde is just a gradient vector times the step size. We take that as an initial value, then apply Newton's method to address this optimization problem. Okay, so this is the line search part. As long as we have line search, we can put down the entire kind of algorithm or pseudocode for this algorithm. So in the first part, we calculate, we have C0, which is initial vector. So we calculate B0. So this step, I mean, if we initialize C to be a very sparse vector, then this calculation is cheap. And we are also given a compression tolerance. Okay, since we need to compress this B. Okay, we will not compress this C, but we will compress the B. Okay, so in the first step of the iteration, we will just take the selected coordinate. We will essentially just select a row of vector. Since we will update rows, each row as a whole, so we will just select a row. And how we select the row is we find the largest entry of this gradient vector and just take that the row of that entry. So that's why we take the L infinity norm of a row vector, and then we find the argmin of that row. Okay. And instead of going through the entire vector, because this gradient is supposed to be of size n, which is exponentially growing, we will just select the connected part from previous iteration. Assume previous iteration we updated the IL, which is the index of row. Then in the next iteration, we will just select from the connected coordinate to IL. Essentially, we mean we treat H as a sparse graph, and then we are actually just moving along the edges. So we will start from one node, then next iteration, we will just look through the connected nodes. Okay, so we're actually doing random work. I mean, not random. We are actually just working on the graph underlying behind the H. Okay, so this is how we select the gradient coordinate. And in the evaluation of this gradient, we need this B and also C. Okay. And next iteration, we'll just do a line search of for alpha, then update the correspond the IL+1 coordinate. Okay, then leave others untouched. So C will be updated without any compression. Okay, and the thing we do compress here is B. Okay, so I mean, since B equals H times C, so H, only one row of H is updated. So we just need to update those J such that HJI is non-zero. Okay, so this will be Bj equal to Bj plus Hji times alpha. And we update it with two kind of conditions. First is that if J is already in on the support of B, essentially means the corresponding row in B is non-zero. Then we update this value without increasing any memory. So we will just do it. Otherwise, I mean, if we need to increase the memory cost, so I mean, if this is not in the support, then when we add new entries, then we will increase the memory cost of B. Then I mean, we add it as long as this value is big, and this is actually a norm value. Okay, we just evaluate two norm. If the two norm of this thing is greater than epsilon, then we update it. Okay, and important thing is that since B is compressed, okay, because some entry of B is not updated. So maybe in the future, a value of B is previously compressed, then the value is not accurate. In order to avoid that, we also redo the calculation of H times Bj, okay, the corresponding updated entry of that. Because this Hij is already calculated here because H is Hermitian matrix. So we just do kind of this inner product, then we can get the accurate value of the IL+1 coordinate of this B. Okay, so with this kind of step helps us to establish one thing, is that if C is non-zero, okay, if a row of C is non-zero, then the corresponding row of Bj will be accurate. Okay, will be accurate value without any approximation. Okay, and the compressed value in B is only those rows that exist in B but does not exist in C. Okay, so here that's why I mean this kind of compression only applies to B, only affects the coordinate selection, does not affect other calculations throughout these algorithms. Okay, and when we have updated C, then we update this kind of C transpose HC and also C transpose C. They are helpful. They will be helpful in the line search, coordinate peak, and also estimate of eigenvalues. Okay, so we will update them, and then we can estimate the eigenvalue via the generalized Rayleigh quotient step. And we will kind of give explicit formula for this kind of update. And since I mean each at the else iteration, or then I mean only one row of C is updated. For example, the ith row of C is up plus alpha. Okay. Then if we check those two quantities, this quantity can be updated in this way. Okay, so previous one plus a alpha times C plus C times alpha, and also plus alpha transpose alpha. Okay, and nothing involves B, so this value will be accurate. Okay, and for the second value, CHC, and if we write it down, we have the previous quantity plus alpha times B plus B times alpha plus H, the diagonal entry of H times alpha alpha. Okay, and these two terms are accurate, and only the middle part. Okay, however, what we did from previous slides is that we, as long as this IL+1, the IL+1's row is in C, then the corresponding value of B is accurate. So this B is also accurate in that sense. So, I mean, as long as we do compression of B according to previous slides, then we have both this kind of quantity very accurate, okay, numerically accurate. Then when we have numerically accurate quantities, then we can do generalized Rayleigh quotients through solving such a linear eigenvalue problem or generalized eigenvalue problem. then we can get a quadratically accurate estimation of the eigenvalues. Okay, this also becomes important if you just want to solve FCI problem for eigenvalues. Okay, because our eigenvalue is quadratically accurate from the iterative, during the iteration. Okay, and how's the data structure? Because such a problem, FCI problem is gigantic. So in the implementation, it's also kind of very important to be careful. And especially we need to careful with the data structure. So here, the Hamiltonian entry are actually evaluated on the fly. Okay, we didn't store any Hamiltonian entries. So we will, as long as we need a one, then we just evaluate them. That's why, that helps us a lot to reduce the memory cost because we do not need to spend any memory storing the Hamiltonian, okay, which is gigantic. And the second thing is C transpose C and C transpose HC, and both of them are K by K matrices. However, since we are doing coordinate descent, so this kind of updating are taking place many iterations. And if we do 10 to the 7 iterations, then they are updated 10 to the 7 times. If we do 10 to the 8, then they are updated 10 to the 8. So if we do too many updates to a single quantity numerically, then there will be numerical error getting into play. Okay, so what we did is we just store these two quantities using high precisions. And this is actually a quadruple position. And then, this makes this value more accurate, kind of be stored more accurately. Okay, the last one is how is B and C stored in memory, because both of them are sparse vectors, and but we need to store those sparse vectors in a more compact way. And the thing we have tried kind of balanced tree and also black red tree, etc. But in the end, we find hash table is most efficient one. Okay, and we will take the configuration string as a key, and then substitute it in hash functions, and we get hash values, and we store things in such a hash table. So we have hash value, and we store key, and we store rows of C together with rows of B. Okay, so C and B are actually stored as a kind of combo. So we combine them together and just store them in a entry of hash table. So this is just hash table, and the entire row is actually the value of the hash table. Okay, so this is how we store things. Okay, and now let's take a look at the complexity per iteration. Okay, if we kind of forget about the number of iterations, then we can count the complexity per iteration. In the coordinate peak, we do not need any Hamiltonian evaluation. We do not need any hash table access. For that part, because in previous iteration, we actually get those kind of value hash table access from the previous update. Okay, so we do not need to re-access those entries. We just reuse what has been saved from previous iteration. And the only cost is just calculating the gradient, which is m squared times n squared times k squared. M squared times n squared is essentially the number of non-zeros column. Okay, so this is the size of the non-zeros times k squared. Okay, and doing exact line search, we need to evaluate the Hamiltonian once. Okay, because we need to get the diagonal entry. So there is a single evaluation of the Hamiltonian, and also access the hash table once. Okay, and the cost will be the number of Newton's step times k squared, k cube. Okay, k cube is inverting those k by k matrix, the cost. And the most expensive step will be updating the vectors. And we need Hamiltonian evaluation on the order of m squared, n squared, and hash table access on the order of m squared, n squared. Okay, and for the other cost to put things together, that will be m squared times n squared times k. Okay, and updating will be just on the k squared and no Hamiltonian and hash table evaluation. So is the generalized rate quotient and k cube for the k by k eigenvalue problem. Okay, we emphasize that although other costs are just looks higher than the hash table and the Hamiltonian evaluation, but since k is relatively small comparing to m and n and also prefactor here, so actually the dominating cost is Hamiltonian evaluation and hash table access. So that's why we separate these two parts. And for the ratio between these two parts, I mean, in our current implementation, this is roughly half-half. We spend roughly 40% of time in Hamiltonian evaluation, 40% time of hash table access. And for the rest 10 or 10 something percent is doing others. So this is the current kind of time distribution among these three parts. Okay. Now let's take a look at some numerical examples. So we have, I mean, essentially here we only have water and nitrogen dimer. Carbon is included in the paper, but not in the not on the slides. Okay, and we compare it against the ISCI, KMC, HCI, DMRG. Okay, and for the this is actually the result from CDFCI ground state. So this is single vector calculation. As we can see, CDFCI is the orange curve. This is decay is most efficient. And HCI is also doing something very efficient. But due to the memory usage, I mean, it stops HCI from going kind of lower. Okay. And DMRG is can achieve kind of very good accuracy. But I mean, regarding the work clock time, it's a little bit slower. And FCI KMC, it's very efficient in the beginning, but later, I mean, it's kind of due to the bias variance trade-off, the convergence is not as efficient as others. Okay, and if we take a look at kind of the excited state calculation, this is still kind of preliminary kind of numerical result. Okay, then if we only have two excited states, then we can see both of them converge very efficiently. If we increase the number of excited states to 6, then I mean all 6 of them converge kind of very efficiently. And let's head up for this part. So as we can see, there is a kind of non-smooth connection here. Okay, and this happens in many of these kind of systems, but does not affect this part very kind of dramatically. But we will see that later. And if we compare it against HCI, the performance of HCI, then this is work clock time. Okay, before we just have coordinate updates versus the evaluation. This is work clock time. And as we can see, I mean, as the accuracy becomes higher, then coordinate descent becomes more efficient. Okay, and last figure is about 12. Okay, and as we can see, one of them is doing something not very good. Okay, and this also, I mean, it's not converging very efficient. And at this stage, although 11 of them already, I mean, achieving very good accuracy, but in order to have the 12th kind of decay, then they pull the others up. Then they after that they kind of converge simultaneously. This is actually also happening here. Okay, this is also happening around here, but does not have that kind of dramatic impact. But as we increase the number of state to 12, then this plays a kind of big thing here. And if we take a look at the convergence against the truncation tolerance, we can see that if we have kind of 10 to the 2, then everything stops here about 10 to the 2 level. If we increase it to 3, then most of things converge to the 3 level, but one of them does not. Okay, 4, I mean, similar thing. And 5, and this is without compression. For water, we can do without compression, but for other systems, we cannot. Okay. Now, if we take a look at the nitrogen dimer, then we can calculate the binding curve with a kind of great accuracy. Okay, and here we use compression tolerance as 10 to the negative 6, and each point is actually accurate up to 6 digits. Okay, so this is 10 to the negative 6 Hartree accuracy. Okay, and DMRG, I mean, from the literature, I mean, this is kind of a few years ago kind of result. DMRG compute a few kind of points up to 10 to the negative 5 accuracy. And since CDFCI is very efficient, so we are able to kind of characterize this binding curve with high accuracy. Okay. And if we extend this such calculation to excited states, then this is what we found for the nitrogen dimer, and this is for 6 states, and this is for 12 states. And the reason I show them here, kind of comparing to the water molecule, is that we do not see those kind of bad 12th eigenvalue convergence here. Okay, So those kind of things only happen for some system at a certain number of excited states, not happen all the time. So for most of systems with small number of excited states, we do not observe that. But still, I mean, that happens in practice. Okay, so we investigate a little bit, and in the end, we think those things are actually comes from Q. Okay, from the rotation, because we have those kind of rotations. So global minimizer is actually not isolated, and if we have a very small eigengap, and the last column will be related to previous columns, then of course, I mean, if we want last columns to converge, then that will affect previous columns. Okay, so I mean, besides those kind of convergence issue, the Q also has another huge impact. Okay, that's also the motivation lead us to update the vector row by row. Okay, the reason is that Q, I mean, actually rotates these kind of things. So if we assume the underlying eigenvectors V are actually very sparse, and then, I mean, if we apply those weight matrix to V, because this is just diagonal and applying a different weight to each column of V, so does not change the sparse pattern. So if this is the V, then we apply this rotation matrix V, then this is still admits the same sparsity pattern. However, if we apply this Q, then this kind of mixing all columns together. So, I mean, sparsity now is given without guarantee. Okay, so in the worst case, Q can mix all columns with nearly equal weights. Then, I mean, the entire block will become non-zero. And the only still sparse pattern are kind of those rows that are entirely empty in previous part. Okay, so that's why, I mean, if we have Q get into play, then updating entries will be less important, because in the end, we will have more dense kind of rows. That's why, I mean, in our CDFCI construction, we just updated the row, and we found those kind of things are still kind of efficient compared to other methods. Okay, and the next reason we want to get into play with Q is due to this kind of bad convergence curve. Okay, that's why, I mean, that's also motivate us to develop the triangularized orthogonalization-free kind of method, and this is joint work with Wiggle and Beecher. Okay, and let's further take a look at, I mean, come back to investigate the objective function. This is objective function, and this is gradient, and this is a gradient descent. Okay, because this step size and this is gradient expression, and we absorb those constant into this gradient step size. And let's unroll it. Okay, let's take a look at this update column by column. Okay, and for the first column, we see that C1 equal to C1 minus alpha times the first part times the second part. Okay, and if we just take a look at the first part, this is a gradient of a single column objective. Okay, and the later part from 2 to k, this is actually mixing all these columns together. Okay, similar thing for the rest. If we take a look at the second column, and if just have these two parts in the gradient, then this is nothing but the gradient of second column for 2 column case. Okay, and the later part is mixing the second with the later k to 3 to k columns. Okay, similar thing to the piece column. Okay, now if we want to eliminate the impact from other columns or from later column, what we can do? We can remove all those later parts. Okay, we can eliminate these things from our updating scheme. And then, I mean, we will have a first column just converging like a single column coordinate descent. So first column will just be a single column version. Second column will be a double column version. And the piece column will be a p column version of the original optimization problem. Okay, and then if we put things back, okay, then this becomes the updating scheme. We just take the upper triangular part of this C transpose C, and then times C. Okay, so this will be the new kind of driven force. Okay, we can also call it fake gradient. Okay, and we can write it using a notation like G. Okay, however, such an updating direction is not a gradient of any energy function. So this becomes a dynamic system instead of a optimization. Okay, instead of minimization of an energy function. Okay, so analysis tool or convergence tool from optimization becomes, not possible here. And we have to introduce dynamic system analysis tool to kind of analyze the convergence, etc. Okay. And hence, the iterative scheme is actually moving in a non-conservative vector field because this becomes not a gradient of energy. Okay. But still, using kind of dynamic system analysis tool, we can still find that all stable fixed point, which means, as long as we are here, there, then we are stuck there, are all form something like this. This is eigenvector times the same thing. And instead of Q, we now only have D here. Okay, and D is just a diagonal entry with entries being positive, negative, 1. Okay, so this is just stretching these columns of V. Okay, then it becomes, if V is sparse, then these stationary points are still sparse. Okay, and if we use C star to denote the set of all stable points, then we can have these two convergence theorems. The first one is for almost all initialization and for small step size, the iteration converges to C for all initialization besides a measure zero set. So for almost all initializations, we can converge to this stable point. So this is a so-called global convergence theory without rate. Okay. And the second one is local convergence. So if we assume alpha is small and the initial error is small, then there exists a polynomial of degree k-1 such that the distance decays something like that. R is the rate of convergence, and since R is kind of linear convergence and P is just polynomial, so this essentially is a linear convergence. Okay. And in addition to the analysis, we can also introduce the some technique to accelerate the iteration. But those kind of acceleration techniques need to be redesigned because now we are no longer a gradient descent method or gradient descent like method because the direction is no longer a gradient. Okay, so we also introduced something like conjugate, but instead of doing things as a whole kind of block vector, now we just do it as a column by column. So we evaluate the weight of the conjugate gradient for each column and also updates the weight for each column. Okay, so both conjugate gradient is kind of conducted column-wise. And for the step size, we're not actually doing column, we're doing kind of more tricky thing. So this tilde means from the first column to the ith column. Okay, so this is still a block column, so is C and V. So this alpha I is actually calculating the minimizing such a thing. So this is kind of more complicated than the regular step size evaluation. And the reason we propose that is that column-wise kind of step size is no longer valid here. And if we do the thing as a whole, just do k columns together, then that step size is not as efficient enough. So that's why, this is the step size strategy we introduced. And since we are doing things column by column, so another good property is that we can also do column locking. So if previous column has already converged, let's say the ground state has already converged, then we do not need to have it get into play in later columns. We can just lock it, okay? And after some kind of perturbation analysis, we also introduce some formula to measure the kind of the locking. This is essentially a locking criteria for such for the ith columns. Okay, and such a scaling is so that all columns can be truncated or locked with the same kind of tolerance to epsilon. Okay. Now let's take a look at the numerical result of this part. And yes.
To say that so the I'm supposed to end it like 425. So you
oh, sorry. Okay, I'm already beyond the time. Okay. All right. Yeah, later we just have some numerical results. Yeah. Yeah. So numerical result shows that the triangular kind of with triangularization, without triangularization, they have similar iteration numbers, but they can achieve different kind of sparsities. Okay, so those are essentially the main message from numerical result. And then for conclusion, we just listed here. We have some conclusion for CDFCI and also TRIOFM. And we just want to emphasize the future work. So we are still developing the CDFCI package, including time reversal, which has already been implemented. But I mean, we don't have time to show the numerical result, and also some reduced density matrix parallelization. And we also recently did an OpenMPI acceleration for the code, and this has some redesign of the algorithm, and we achieved roughly 10 times speed up comparing to the single thread. Comparing to the previous multi-thread one. So I mean, previously we did the longest numerical example we have is roughly takes 14 days. Now we can get that result within 1 day. Okay, and also another future work will be kind of taking this triangular OFM plus coordinate descent, so that this becomes a practical method for full CI problem for practice. So that's it. Sorry, I mean the time is a little bit kind of beyond.
Thank you.